Well, while the screens are loading, hi everyone, my name is Bianca Furtuna and I'm an applied data scientist, machine learning scientist at Microsoft, and I normally work on customer projects and apply different techniques on different customer data. I work across industry, so it can be absolutely anything. So if you're interested in that, we can chat a bit more after the talk. So normally I'm like very loud, but I have a cold today, so my voice is a little bit under edge. So I'm going to be very slow, and I'm going to try not to cough too often. Normally I run these sessions quite interactively, so if you have a question, do raise your hand and we can talk about it at that particular moment in time. And as always, there's questions at the end. So what I'm going to talk about today is this idea of model explainability and interpretability, and more importantly, what are the current techniques that are out there and how you can use them in a practical sense. And also, I'm going to try to speak very broadly on how I personally have used them on some projects before. So let's talk about this idea of model interpretability. This is becoming a very overlooked term because nobody really knows what it actually means. So I think everybody sort of has an intuition of what an interpretable model can be, but I'm not sure everyone's definition is the same. So there's actually a very, very interesting paper called The Mythos of Model Interpretability, where a couple of researchers are trying to bring all of these definitions together. So I linked it in the slides, so if you're more interested in that, you have a read. But generally, it's all about this idea of explaining why your model is behaving in a certain way. It's about being able to easily understand the model behavior from a human perspective. So sometimes you see with machine learning these like really complicated graphs, and if you have deep learning like 200 neurons that activates, and you look at it, it's like, oh, it's doing something, I'm not sure what. So it's putting it in words or something that's very easy for the human to comprehend. It's all about establishing trust. So if you can understand how the model is behaving at a global level, or even at like a very local level, you can start trusting it more rather than thinking about it as a black box. Transparency, so knowing how the model that we deploy out in the world are operating in unforeseen circumstances is very, very important. Causality, again, this is very, very important, and it's something that is not actually touched in data science very much. And it's about being able to take interpretable decisions. And a really good example of that is, we talk a lot about how data science and machine learning is going to revolutionize stuff like healthcare, for example, where these automated decisions or even like advanced medical practitioners are going to impact in a really big way human lives. How are we going to be able to make sure that doesn't go wrong? And again, the standard argument is, well, we're going to have like human supervision. But what happens when the model got it right all the time for like 2 years and then suddenly makes a mistake? Maybe that human started being accustomed to the model being right all the time. So it's not like paying as much attention. And you see that happening a lot, for example, in some autonomous driving examples. So I wanted to go through certain terms that I'm going to use a lot throughout this talk. This idea of global versus local explanation. So a global explanation will be, I have a machine learning model. My machine learning model takes this sort of decision in this case. So it's about the general behavior of the actual model versus local explanation. I have this one input to my model, and I'm making an explanation for a particular prediction. Model agnostic versus model specific. So a model agnostic type of technique can take in any model whatsoever and give you explanations of the back of it. And also model-specific is something like you'll have a technique that only works for neural network, or you'll have a technique that only works for decision trees, so on and so forth. It's mostly neural network in this category. And also it's about explanation coverage. So when we talk about local explanations, that's the coverage is the region in the input space that the explanation applies to. So you have your input space, that explanation covers a particular region, and we're going to get more details about that as we progress. Now, a question for the audience, and it would be really great to get some of this participation on this. So which of the following models or algorithms are interpretable? K-nearest neighbor, linear regression, neural networks, decision tree classifiers, or vector machines. And take this? Depends. Yes?
Linear regression.
Sorry?
Linear regression and decision trees are usually the most intuitive one.
Yeah. So that one was linear regression, and decision trees are normally the most interpretable one, and then the rest continues. There was also another hand.
Generally speaking, neural networks are described as black box, so the most difficult.
Yeah, so neural networks described as black box and most difficult. We got probably an architect's question there, because it always depends. So that's the right answer. So it does highly depend. I think a lot of people have the perception that linear regression or something like a decision tree is interpretable out of the box. But how are you going to interpret a linear regression that has 100 parameters? Are you going to manually start putting them down and like figure out how they weigh themselves up? It actually becomes too complicated, really complicated. It's very easy if you have 10 parameters, if you have a decision tree that has like 2 levels and a couple of leaps. But if you get into an ensemble, if you have an ensemble of decision trees like a random forest with 100 trees, are you actually going to look for every single tree? Probably not. So that's why we have the sort of models and techniques for interpretability to try to understand. Think about it as a way of summarizing all of that information. Then you can dig yourself in a quick and easy manner. So the focus on this talk is on local explanations and also model agnostic explanations. So I'm going to cover 2 techniques. One of them is called line, and the other one is called anchors. I'm going to sort of at a high, medium level try to explain what they do. And then give some pros and cons and some examples of how you can actually use this in practice. So, what is line? Line stands for locally interpretable model agnostic explanations. So the goal of line is to identify an interpretable model over the interpretable representation that is locally faithful to the classifier. And God, that's a mouthful, right? Like, a lot is happening. So let's break it down of what this technique actually does, and then hopefully you'll be able to very quickly see the pros and cons of this particular method. So again, this is a local method, so it works at the prediction level, so you normally take an input. So that's, let's think, an image, a row you're trying to predict, the sentence you want to classify to positive, negative, so on and so forth. Then the algorithm will take that input, we'll do a couple of input perturbation. So, for example, if it's an image, you're going to cover parts of the image and put other things in between, so on and so forth. You're going to extract the model predictions for the input perturbations. Then you're going to take this perturbations and the model predictions. You're going to build an interpretable model. In this case, it's a linear model with very few parameters that, as a human, you can very quickly understand. And then you're going to construct the explanations and present them to the user in a quick and easy format. Right? Any questions so far? Okay. In a visual format, this is basically what you do. So imagine that the red cross is your inputs. So this is the input space you're looking for. For simplicity, is represented in 2 dimensions. The input you're interested in is the red cross, and you're essentially perturbing this input in the area. Every single point is weighted, so as you can see, it's bigger based on how close it is to your original input. And basically then you're just doing a linear model, which in this case is a line, to learn what the local decision boundary is for that particular input. So the intuition is really, really simple in this case. A couple of things that can go wrong, or a couple of things that are very difficult in this case. Not every single data or input distribution is linear, even locally. So you can have some very, very complex nonlinear decision boundaries, and this is not going to work very well for that. Also, you need to represent the input space in order to be able to get this perturbation systematically. You need to be able to represent them in a certain way, and that can be limiting, right? So for images, you have this idea of like superpixels, so you break the image down in this like big portions of the image, and then you like cover some of them up, and that's good, but it doesn't really capture the variation. So normally maybe you want to like identify the background and then gray it out, or change the color of someone's face, like that sort of thing, and you can't really do that with this method. Yes?
So I was wondering with the superpixels, so would you be splitting the image into different superpixels per explanation, or would you be using the same superpixels across?
Yeah, that's a great question. So the question is, for something like superpixels, would you be splitting the image in the same superpixel every time, or would you be using different ones? So in line case, they're actually using an algorithm called superpixels, and they're going to be different for images, supposed to identify different regions of the image that are of like different importance. So in theory, the background should be in the same superpixel. Yes?
How do you select the samples for the input space? Are you selecting all the other samples, or is it subset?
So the question is, how do you select the sample for the perturbations?
Yes.
Yes. So it's a sampling method. So they implemented as part of this library, and it's different from every single type of data. So I have a slide on that, so we're going to see more information. But it's just a random sample most of the time, due to computation reasons as well. Of course, you can't take like 3 million of these. You need to like subset it to a handful. So there's actually, in this particular paper, they do describe a technique which is called submodular pick. That's sort of looking at what samples would give you like the best value for your perturbation. Something like that, I guess I can call it. But we can cover that either in the paper or afterwards we can talk more about it. Yeah, any more questions? Cool. Okay, let's carry on. So anchors. So quick introduction to anchors. So anchors is the next iteration of line. It's by exactly the same authors. And it's trying to actually take some of the prompts from line and trying to address those. So an anchor is a rule that essentially anchors the prediction locally, such that in the instances where the anchor holds, the prediction is consistent. In other words, if you have the presence of an anchor in your input, that means almost all the time, consistently, there's a high chance that your prediction is going to stay the same. A quick example, like if you have a model that does sentiment analysis, is taking a sentence in and is putting neutral, negative, or positive, having the word not good in it. If you have those two words, almost all the time that sentence is going to be negative. So I had to do mental thinking about that one. So is that sort of thing. It's basically looking at the smallest condition that is required for the prediction to always be the same. So this algorithm at very high level works like this. So we generate potential anchor candidates. Again, very similarly for every type of problem domain, we need to define what an anchor is. So for example, for the image domain, you're going to have the superpixel, present or absent. I have a list of that we're going to talk in a moment. But you basically generate potential anchor candidates. Start with an empty set, generate potential anchor candidates. So for example, you say it's actually the superpixel in the center for an image. Then you identify the candidate role with the highest precision. Does the candidate meet the anchor definition? So the anchor definition is you need to have high precision, i.e. when this anchor is present almost all the time, does the prediction stay the same? And highest coverage, does it cover a very wide range of the input space? If the answer to that question is yes, then you identify the anchor and terminate, all is good. If not, you go around and do this with multiple times. So now let's look visually about the difference between anchors and line. So let's say you have that particular decision boundary. What line would do is basically have a point, it will sample around it and then fit a linear model around that point. What anchor is basically look for that space around your input spot where the prediction holds. And that's basically the visual example for that. Any questions on that?
So does anchor quantify how big that space is?
Yes. So it's all quantified, i.e. the actual package library does return your coverage number.
What does D mean?
Sorry?
What does D mean? Diameter?
Yeah, it's just like diameter. So that's also like basically the distribution you take samples in and everything like that. Cool. So let's look at, so I touched upon this before, but let's just write it down because it's always easier. So one of the maybe challenges with these two methods is that you do need to define what a perturbation is and what is the representation that you're looking for each single data type, right? Because they are different, so you need to represent them in a different way. So for tabular data, for example, tabular data is everything you can fit in a table, right? Think about it as a table row columns, that's the tabular data. So the perturbation in this case is fixing some features and sample the rest of the rows. So for example, if you have, a very common data set, if you have the adult income data set, so the one where you have a couple of characteristics and you're trying to predict if the income is below and above 50K, you would fix stuff like civil status and years in employment, and then you will sample the rest randomly, right? So that's how you would like change the input space. And then the interpretable representation is essentially this feature. So it's quite straightforward for this particular case. So think about it as something that you get out of the decision tree. If years in job is less than 5 and status equal married and stuff like that, that's basically your interpretable representation, and that's something that we as humans can understand. In terms of images, there's this idea of superpixels. So first you apply the superpixel algorithm, extract the superpixels, you turn them on and off. So in line, what they do is they take the superpixels and they turn them gray. In anchors, what they do is they turn off the superpixels and then they take some other random images and they put it in there. So if you have a look at this example, they're really funny. You sort of see the head of the dog with like a Union Jack around it. It's like, can you detect it? Maybe, maybe not. So that's actually like very interesting because those perturbations are a lot more interesting in the anchor's case. And then, again, the interpretable representation is the presence or absence of the superpixel. So visually, it's going to give you like this part of the image is what leads to the prediction. So if you have a dog, it's something like the head of the dog is what leads to this prediction of dog to be made. And this thing has had quite a bit of success in some image classification. So for example, they applied it to this neural network that was identifying wolves and dogs, so trying to discriminate between the two. And they actually found out that what the model learned was the snow in the background. And they were able to do that by using that method because they were turning the superpixels on and off. So it can be very useful for that particular type of problem. Okay, text classification. So this is another different problem because your vocabulary can be so long in a text classification problem. What you do is fix some tokens of words and then replace the rest by random words. And the interpretable representation is the presence or absence of tokens in that particular sentence. So as the example I gave before, having not good in a sentence sort of ensures that has negative sentiments all the time. Any questions? No, fantastic. Okay, so let's actually look at some actual examples. Okay, fantastic. So what I'm going to show here is both Lime and Anchor's explanations for tabular data. This example is actually just using the pure GitHub code. It's not using any additional libraries. So now both Lime and Anchors are in a lot of other libraries, but here's sort of using the original ones. So what I'm going to do here is very, very quickly, and again, do stop me if there's something that is unclear. So it's loading the iris dataset from scikit-learn. It's preparing this data set, doing your typical train test splits. It's loading a gradient boosting classifier. It's doing 20 estimators on top of it, so it's definitely not interpretable. I mean, it is if you really try, but out of the box is not. So let's look at the confusion matrix. Of course, this model is like very simplistic, so gradient boosted decision tree classifier can learn it very, very well. Like the confusion matrix is shown there. We have a fantastic 95% accuracy, 96% precision, and sort of 95% recall. If I did this every day, that would be fabulous, but you know, this is just a toy example. And there's another thing that, let me see if I can make this smaller so you can actually see. So the decision, the scikit-learn always also allows you to compute the feature importance for the particular things that you have. So for the iris classification, you can see that the two most important features are petal length and petal width. So this is what traditionally you would do if you wanted to understand what your model was doing. You say, okay, having variation in these two features is probably going to make the biggest difference. So how to use Lime? It's actually like quite straightforward. So you import a Lime library, you load the right type of Lime explainer, so in this case it's tabular because it's tabular data. You need to provide it your data frame to have an example of what exactly it's looking for, the feature name, so on and so forth, in order to be able to have these explanations. So we're going to test this this explainer with sample number 10. And you can see the explanations here. So this is what the line explainer gives you out of the box. It gives you the prediction probability for every single one of your 3 classes. And it's saying it's like 92% likely that this is versicolor. And the 2 most important reasons why this is that is the petal length and petal width. And guess what? We're consistent with the feature importance from the above. And it also gives you the values for that particular one. So in this case, it's 4.5 or 1.5. So this is really good, right? This is good. It gives you an explanation. Can anyone detect any potential issues with these visuals and these explanations? Other than it's very pretty. Okay, so a lot of the time, this is good and gives you an intuition what is happening in that local area. But sometimes the numbers there on the particular reason why this class was chosen are like quite random. I.e., they don't add up to 1, they don't add up to anything. Sometimes they're like very random, so it's really hard to understand exactly why that is happening. Anchors. So again, this is using the anchors library. In terms of tabular data, there is a requirement for it to be discretized. So it's basically putting it into buckets in order for it to run. So I have done that. So it's actually quite easy. It's following the scikit-learn API very closely. So you just need to fit this explainer on top of your training data, and then you build your model, you train your model on top of that transformed data. So because the data is slightly different, you have to plot it again. So this model is very similar to the other one. As you can see, the petal length and petal width are the most important features. And then let's try to get the explanation for this. So as you get the explanation for this, you can sort of see the difference here. So the anchor return is that sepal width is smaller than 3, and petal length is smaller than 5.1, and petal width is bigger. So here sort of gives you the entire condition. Also look at partial anchors. So partial anchors is just like part of that. So let's say we just take the first 2 parts. So petal width smaller than 3 and petal length smaller than 4.5, and then you can get the partial precision and coverage in this case. And again, it gives you a really good intuition about what your model is doing. Any questions on this? Okay. Fantastic. So I briefly touched upon this. So these techniques, again, they're like quite new. So Line came out in 2016 and Anchors came out in 2018. So there's still a lot of research and investigation that has to be done in this topic. So they're definitely not the things people are going to use in 5 to 10 years' time. But they're very useful. And 2 areas that I found very useful when we do deploy models into production is this idea of model debugging and validation. Making sure your models work. And this is on top of just traditional validation, your like accuracy, precision, recall, inference, or like you name it. There's like so many metrics, but they are just numbers. This type of techniques allow you to do model debugging and validation in a slightly different way. And then you can start looking around at these perturbations and trying to understand if your model is stable enough. And again, model understanding, trying to understand how your model operates. So the example I gave with the model that discriminates between a dog and a wolf, if they use this technique, they will have figured out something is wrong. And once you have that knowledge, you can then start to fixing it. So some pros and cons of these techniques. The problem is that it's very easy to use with existing models. So honestly, like to make line or anchors work in your current pipeline and data science cycle, it's like takes like 10 minutes. You have nothing to lose. You can easily use them with your existing methods. It does give you an intuition about the model behavior locally, model understanding before deployment, and it's really good model validation tools in addition to the traditional metrics we use in the field. Cons for Lime is that it does build a linear model, and the local boundary can be highly linear, especially in very complex problem. It does not return any coverage information, while Anchor does. It cannot be very easy to interpret in a lot of cases, but it does give you something you can compare between different examples and potentially build your own baseline. In practice, they don't work well for all examples, so they work really, really well for certain cases, but they don't work as well for others. So it's very important to understand that they are not bulletproof. They're new techniques, and people are starting to experiment with them. There's no global understanding of what the model has learned overall, right? So we're having an understanding of these local predictions, and it's good if you do validation of a couple of very important ones or trying to think, like unit tests. So have your edge cases where you never know what's coming. So you have no global understanding of what the model has learned overall. And yeah, another challenge is that you do need a perturbation distribution that needs to be defined for every domain. In some cases, this is quite restrictive. Right, so I'm gonna make the slides available afterwards. Yeah, that's okay. So there's a lot of resources here. Again, the first paper is very good. It doesn't have math or anything in it. It just talks about what modern interpretability is. And before I read, I was like, interpretability makes sense. I know what interpretable model is. And then I read it, and I was like, I have no idea. I don't really know, so that's good. SHAP. This is a different technique that is very similar. Well, so of the paper of Lime and the authors of SHAP, they essentially say that Lime is a version of SHAP, so they have a lot of theoretical definitions for them. However, the SHAP explanations are quite complicated to approximate and compute, but they do have a great library to use as well. And then there's a lot of different resources and framework that everybody that's interested can then look at. Thank you. Any questions? No? Yeah?
As I understand, Lime can be quite unstable for some particular models and types of data. How would you determine if Lime is giving you robust results?
That's actually a really good question. So the question is, it looks like Lime is quite unstable. How would you detect if it's robust for your type of data? So a good way is to run some sort of experiment on top of it. So look around, you can make your own perturbation of data and see what's happening. And then if the prediction and explanations are quite similar, or they are sort of converging, then that's a good way to know it's quite stable. I just flipping the things around, or looking in that particular area, or something that you would expect from your experience or domain knowledge to be exactly the same. Lime should give you consistent results. If it doesn't, it's either a problem with your model or a problem with Lime. Any more questions? Yeah?
Do you have an example working with time series data, for example, trying to put an LSTM one-line detection?
So the model doesn't matter. So it can be LSTM, it can be anything. So yes. So the example is, it's because you're looking at the prediction, right? So you'll put that particular time slot as your model. As long as your model is, you can curate it to get predictions of the variation, then yeah, it should be good. It's exactly like the same as tabular data, exactly, you just need to format it slightly differently, but it's exactly the same.
Are there any reasons to use line with Anchor as